Today's webinar presented by Líbilo software. Today we'll be working in our structural analysis and design software RFEM 6. The topic for today's presentation is Revit and RFEM 6 data exchange. My name is Amy Heilig. I'll be your moderator, answering any questions you may have. I'm the CEO of the US office and also a sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your presenter. He's a support engineer also located in our Philadelphia office. You can go ahead and adjust the GoToWebinar settings with the dialog box as shown here. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. And with that said, I'll go ahead and turn it over to Alex for the remainder of our presentation today.
Great, thank you for the introduction, Amy. Yeah, so here is the content for today's webinar and what I'll be going over. So it's broken up into 7 sections, but the first 4 or 5 are kind of the first half of the webinar, and then 6 and 7 are the second half. So first, I will be introducing the Revit model that I've prepared for today's webinar, and then I will show how to create the analytical model within Revit, export that from Revit to RFEM 6 model, or in RFEM 6, I'll show you how to create the model so you can run the results and add updates. Then I'll export that and show how to import it into Revit with the direct link. And then the remainder, or the other half, will be going over data exchange with IFC between Revit and RFEM 6. And then I'll go through an introduction to the nodal links. So now I will switch over to Revit, and here is the model that I've prepared. So it's a basic steel structure consisting of steel frames with some coupling members and some X-bracing. You can see that for my column, I have my cross sections. So most of these are all W shapes, and then I have steel 8992 for the W shapes, and then I have my X bracing assigned. And this is the structure that you would create, for probably from the architect. And the plan is to help the structural engineer by exporting this structure to RFEM 6. And so to do that, first we want to go into the Líbilo tab. And this tab, or our Líbilo plugin, is our direct link. And this is what you will want to install after installing Revit. It needs to be installed manually. But once you do, you'll have these 6 buttons here. And the first 2 buttons are for exporting and importing the model between RFEM. Then you also have the same options, but for RSTOB or other program. And then you have these last 2 buttons. The main one is the conversion tables. So I'm going to open up the conversion tables and just go over these quickly. So the conversion tables are what map the sections and materials between Revit and RFEM. Since Revit and RFEM don't share the same section names and materials, they need to be linked together. And so this is what the conversion tables are for. And they're really easy. Once you set them up, you don't have to set them up again. And you can even share the file of these conversion tables with colleagues. So not everyone has to set them up. You can share the file. And all you really need to do is type in the Revit name or the material or section name that's in Revit, and then type in the name and how it appears in our Líbilo software programs. So I have that set up and mapped for my model. So let's get into creating the analytical model for Revit 2025. So right now, what we're looking at is the physical model. Basically, all these members are solids, basically, and they have, the perimeter lines, and they're made up of a bunch of lines and surfaces as solids. And so what we want is the analytical lines, or the analytical model, which is the center lines for each of these members. And that's what we were trying to export into RFEM. And so Revit used to create the analytical model automatically up until Revit 2023. But now for 2024 and beyond, for 2025, this needs to be done manually. And so this is what I want to show in this example model. So to do this, first we'll go to the Analyze tab. And under the Analyze tab, there's a button here called Analytical Automation. And so this is what's going to help us create that analytical model. So here you can see the first option is we can go from an analytical model to a physical model, or we can go from a physical model to an analytical model. And this is the option we want to go with today. So I'll click on that, and then you'll see some additional options come up. So the first thing we want to do is select what we want to convert graphically. So I will select that graphically in Revit. And now that that's selected, we have a next option here. This is a tolerance. So right now, this custom tolerance, this is basically what if a member member is within this tolerance, then it will be connected. So the analytical member will be connected within this tolerance. This is based off of a length, and my units right now are in feet, so this is 1 foot. So let me open also the analytical model and put them side by side. And so let's run this to see what 1 foot looks like. And so I've created, so you can see the analytical model based off that 1 foot tolerance has been generated. And you can see that my coupling members here connected to the beam because they're within that 1 foot. You can also notice some other members have also done the same. So sorry about that. If we change this to something like 0.8 feet and run it, now you can see that those members have straightened out and everything looks better, but you'll notice that my coupling members are still kind of floating here, and some of these other members aren't completely straight. And also I have this cantilever at the end of my column as well. So there's another option we can use to fix that, and that is the adjust analytical elements to nearest level. And once I turn that option on and run it, we'll see what that looks like. So that'll adjust all the members to the levels that are created in Revit. For example, if I look at the west view, so all of the members or all the analytical lines will now be adjusted to these levels. And so, so now everything looks better. Everything is straight and all of my members are connected and everything looks good. The only issue with this is now it's not super optimal because my analytical lines are now resting on the flanges of my beams, whereas I would like these analytical lines to be in the center of my beams. So what I can do is there is another option that can help with this, and that is called consider only levels with structural parameter checked. So I can check this on, and all of my analytical lines will adjust to any level. If I click on one of these levels, any level that has this structure option turned on. So what I'll do to utilize this option is I'll create some copies of my levels and activate that option. So this first level, I'll just go through, create a copy, and then I'm going to move that copy down like so. And with that copy, I'm going to rename it. and I'm going to check on the option structural. So then I'll do the same thing with this level. Create a copy, move it down, rename it, and check on that option. And then we can do the same thing for this last level. Like so. Okay, so now once those are created, now we can open that panel back up, and we can turn on consider only levels with structural parameter checked. Now this option does also come with another tolerance. So let's see what it looks like. For example, if I exaggerate that tolerance, we can see how the tolerance works. So if I turn that on, you can see that members down here have been sucked up into this level tolerant, into this level, because they're within that 10 feet that I entered. So that's not a great value. So what if I do something too small? Now you can see that my couple of members didn't get into the level. Some things aren't in there. So the best thing to do, I mean, well, one is the good happy medium. So we'll run it with 1, but that's how that tolerance works. And so now our analytical model is created. And now you can see that my analytical lines are within the center of my beam. And yeah, everything is connected, all my cross bracing, they're all meeting at the same joints and everything. So that's good. So that's how you can create an analytical model within Revit using that tool. So yeah, now that we have our analytical model, there is some other model data that you can add into this. So you can also add in boundary conditions. So if I go back under Analyze and Boundary Conditions, I could add in some point, line, or area supports in my analytical model. I can also add in loading. You can put loading in, so point loads, line loads, and area loads. Or along with load cases, you can also create load cases and load combinations. And so all of this info can be carried over into RFEM. So if you wanted to have your Revit model be your all-in-one model, where you're doing your architectural detailing and also running the structural, or creating the structural info, you can do that. Or you can simply just leave it up to the structural engineer and just export it into RFEM, the analytical model. But totally up to you. So now we'll go over exporting this to RFEM. So I'm going to move my windows over, and so we'll go up to the Líbilo and we'll go to export model. And so yeah, we want to export this model to RFEM 6. You can either create a new structure and have RFEM create a new file and import the model in, or you can overwrite an existing structure. I'm going to create a new structure or have RFEM create a new file. And on top of that, I can also have RFEM open up a previously saved template. So I have a template that I've created from a previous model, and it's really easy to do when you have the model that you want to use as a template. It could be even a blank model. You can go to File and then Save as Template. And then all you need to do in Revit here or in the Líbilo plugin is point your computer to wherever that file is, wherever that template is saved. And so now when it opens a new file, it'll open that template. So it's not a completely blank file. And yeah, that's great if you want to save like load combinations or anything. And so yeah, then also I can set the Z direction to upward. That's what I'll keep it as. You can choose between the analytical, physical, or both to export. I'm going to choose the physical, and the reason really doesn't matter, but the physical model and the analytical model in Revit can have different model data, you could have the analytical have different sections of materials compared to the physical. So I'm going to choose the physical because it keeps the member rotations correct, which is good. Objects to transfer, you could only transfer selected objects if you like, only visible ones. So you can play around with that. And then lastly, the grid can be exported. I'm not going to though. Second tab, model data. I'm exporting model data. You can export the loads, like I said. I don't have any defined, so I'm not going to. And so, yeah. So now once I click OK, that'll start the process of exporting. And this is where Revit and RFEM communicate with each other via API. This is a good time to mention that both programs do need to be installed on the same PC. This is a requirement of the Líbilo plugin. But now that the export is done, we can now see the model over here in RFEM. So yeah, the model has been imported. And the first thing that's always good to do when you first import a model is to check it visually. You can check and see and make sure that you can see my materials have been correctly mapped over along with all of my sections. And there's also tools within RFEM that can help you do some model checks. If we go up here to tools and then model check and then identical node, this can check for identical nodes within this tolerance. So if there's any nodes, more than one, that lie within this tolerance, then they'll show up here. So for example, if I type in 5 feet, you can see what that looks like and how it detects the nodes. And then you can choose what you want to do with those identical nodes. The other tool we have for model check is the overlapping members. So we can also check for overlapping members. I don't have any, but that's always a good thing to check for. And yeah, so now with this model, what we want to do is prepare to run a simple self-weight check or self-weight load, just so we can check the results. To get a better understanding, looking at the structure, I'm going to render it according to the section views. So I can go over here to cross-section, and I can get a nice view of each of my cross-sections that are color-coded. You can change the color of any of these. And so that's a good render. We can also render it according to member type. So I can see all of my members are set to beam. And then another good one is member hinge. So I can see that I don't have any member hinges defined. So all of my connections right now are completely rigid and all 6 degrees of freedom. So now I would like to edit some of my member types. So I'm going to go to my views here. I'm going to change this back to member type, and I'm going to isolate my cross bracing. So I'm going to highlight all of those and change them to tension. So now these members can only take tension forces. Next, I want to change all of my coupling members to truss. So I'm going to highlight all of my coupling members and change them to truss. So now those members cannot transfer moments. They have a pin connection. And now lastly, I would also like to apply hinges to my wall and center columns. So I will create or show those. So yeah, I would only like to apply some member hinges since we have pin connections here at the top of my columns. I just realized I forgot to mention the connections. Yes, I have some connections defined in Revit. So for the columns and beams, I have some plates and fasteners, and then the columns framing into the beams here are pin connections. So I'd like to consider that in RFEM. So I'm going to go to the data navigator, and I can go under types for members and double click on member hinges. And so I'm going to create a new member hinge. It's a moment release. And then I can simply just assign these member hinges to the tops of my members here. I'm going to click OK again. And so now you can see those pins, or these white pins at the top, telling me I have member hinges there. And now under the member hinges display, you can also see what that looks like with member hinges assigned. And lastly, before we can run the calculation, I am going to exit out of this view. And I also need to add nodal supports to the bottom. So I'll create or assign a nodal support, a hinged one, and highlight all of my nodes there. And yeah, so now this structure is ready to run a self-weight load case. So I'm going to run the calculation. And it's done. So now you can see the best thing to do really is to check the deformations. Deformations really tell you a lot about the structure. And right now ours are looking good. I can change this to colored section and a wireframe render. Right now we're getting a max of 0.07 inches, which is in our coupling members. So we can check the deformation. We can also check the member internal forces, like the axial forces on the columns. We can see the moments on our frames here. So I can isolate those and get a better view. So we can see we get our positive moments within the center spans, negative moments where our columns are framing into. So it looks like everything is good and correct with our model. So that's good to see. So theoretically, the next steps for this model would be to add in some more load cases, add in some more loading, have those load combinations created automatically, and then run through the design with our design add-ons. And so I'm not going to do that with this model today to save time. I would like to move forward and import this model back into Revit. So let's say you ran the design and you changed some section sizes or materials, and you want to update that in the Revit model, which can be done. It is possible to just simply update sections of materials within the Revit model. If you did make any geometrical changes, then you would want to just simply import the whole model back in. And so I'm going to delete my Revit model and then go up here to import model. And so again, we want to update the existing structure. We can't create a new file within Revit automatically. You can import the analytical model or the physical model, or both, the analytical and physical properties. I'm going to choose both. And yeah, then here's the option where if you only wanted to update only materials, thicknesses, and sections. So that option is there if you don't want to wipe or delete the model in Revit. And so now I can run that import. And so you'll see the status down there in the bottom left of RFEM. And this window is what it'll look like if you don't map every section in the conversion tables within Revit. And this will simply come up. So it's saying that my cross bracing section is not mapped to anything. And it's really easy to just simply, any of the families you have installed, you can simply just go down and choose that section and hit apply and map them there if you don't have them in the conversion table. So yeah, so import has succeeded, and you can see we have imported both the physical and the analytical models. And it's great because if I show the analytical model, I have my nodal supports in there automatically from RFEM. So all of that model data in RFEM can be saved in here. I can even check my members And I can see with my members, I have my member end conditions. So those hinges, even from the trust members we defined in here, come in. You can change the degrees of freedom for these supports if you wanted to here. And yeah, that's all of that info comes with the analytical model. And so that's basically the Líbilo link. That's how you can use the Líbilo link and import and export models and analyze them between Revit and RFEM. So next, I would like to go over the data exchange using IFC. Okay, so often Revit and RFEM 6 are not being used on the same PC. As far as we know, Revit cannot simply export the analytical model via a shared file extension. So therefore, we can just focus on the physical model and exporting that as in the IFC format. So let's open up here, File. We can go to Export, and we can hit IFC. We can choose where we want to export that IFC on our computers. And then we can choose which IFC version or type we would like to use. Right now, we just support IFC 4 reference view and IFC 3 coordination view. So I'm going to choose IFC reference view and run that export. And it's pretty quick. Now I can go to that file on my computer and I can open it up in BIM Viewer. So once open in BIM Viewer, it's everything, comes with it. The connections, all of my connections are here. I click on a member and I can see every member comes with the section that was assigned to it, along with the material. So all of that info gets transferred through the IFC, which is great. And so now I would like to import this into RFEM 6. So I'm going to open up RFEM 6 and I'm going to go to File and create a new file. And then I'm going to name this file IFC import Revit. Click OK and create that new file. And so now I can go to File, Import, and Import IFC. I'll choose that IFC I just created. Click OK. You can check or decide what coordinates you want the model to be placed on. And yeah, so now that IFC model is now within RFEM. So what we can do is now you can see I have all of that IFC info on the left-hand side here. I can even click on a member and turn on my IFC properties panel on the right-hand side here. You can see all of that IFC info comes with it, the section name, also the associated material. So materials and sections come with this, which is great. And yeah, so right now though, the problem is that this is just, these are just IFC objects. If I go into my project manager or navigator, data navigator, you can see I don't actually have any RFEM elements. I don't have any members or anything. So what we need to do is convert this IFC model into an actual RFEM model. And to do that, we also have a conversion table with an RFEM. So if I go up here to CAD BIM and open my conversion tables, we have the external name here along with the mapped material name, and under sections, the same thing. So it's really easy. And again, you don't have to even set this up, but if you don't, then you have to assign these sections and materials manually. But it's really easy to set this up. With this cell here, you can simply use this graphical button to select the section or material name within the IFC properties. You can type it in manually. You can create an XML file and save the XML file and share that with colleagues. And you only have to do this once. So it's really quite simple to set up. You can have multiple conversion tables. And so, yeah, so I set this up, and yeah, and then in this cell, you can simply either go into the material or cross-section library that RFEM has, and that's how you can get the name. So you don't even need to like know the delivable name. So yeah, it's pretty simple. So I have that set up. And so now what I can do is I can just hide these IFC elements that I don't need anymore. We'll hide the connections and fasteners. You could convert these connections and fasteners into, or probably mostly just the fasteners, into straight elements if you wanted to, but it's not really practical. So I'm going to hide all of them. I can't hide these end plates here because they're linked to my cross bracing. That can be changed in any IFC file, but for mine, it's a little bit different. So I'm just going to hide my plates here, like so. And yeah, so now we have just the model, or well, just the members we want to convert. So now I can simply just highlight this whole model and right click on one of the elements. You'll see we have a couple options for the IFC conversion. You can convert into straight or curved members, convert the element into a surface, or convert it into a solid. So I'm going to convert it into a straight member. And so now all of my members have been converted. All of my sections, again, are mapped to the correct members and along with my materials. So now I can hide all of my IFC elements, and now we can just simply, again, work with the model in RFEM. Now, the issue is that we still have the gaps here. So everything is laid out the same as it would be in the IFC model. So that gap there is because we had the plate there. And so all of those gaps are going to still be there. And that means that if we change this into a wireframe view, that none of our elements are actually connected in the eyes of RFEM. Everything has that space, that eccentricity, which can be a bit of a blessing and a curse, as you'll see. But there are a couple of ways. So the next steps would be to connect these elements. And there are a couple of ways to connect them. The first option for connecting these elements would be to use the tool down here called the Extend Lines Graphically tool. So if I click on that, it'll essentially extend the lines, and they have to be in the same plane, but it'll extend them and it'll connect them like so. So you could go around and connect elements like that. But the issue with this option is that what do we do with these coupling members up here connecting to my beam? They're not in the same plane. What you could do is select them and go to the move/copy tool, and you could simply move these elements into the same plane, like so, like that. And then use the extend copy tool and extend them and connect them to the beam. So this is the first option. You can use the extend tool and connect everything and go around. But what I want to show is an alternative to this. And the alternative is an object we call nodal links. So if I go under my base or my navigator, data navigator here, and go under types for nodes, I can double click on nodal links. And this is what the nodal links dialog box looks like. And so basically, we can assign these nodal links to nodes. And once they're assigned, those nodes will look for other either nodes, members, or surfaces within this search radius here. And so, yeah, you can set the search radius to anything. Then there's also the search method. And with the search method, right now, it'll just search for the closest objects. And in the future, we are thinking about adding other options to include here. But yeah, currently the only method is to search for the closest objects. And we have an option down here for adding member hinges automatically to the start or end of these nodal links, as well as excluding objects or including related objects. So with that said, now I would like to create some nodal links. So the first nodal links, I'm going to connect my beams here of my main steel frames to the columns. And so I'm going to uncheck nodes and check members. And then I'm going to go up here to assign to, which is where we'll assign or choose the nodes we would like to assign. And I'm going to create a visibility of just my beams and my columns. And then with this button, usually this is turned on, called ignore related objects. I'm going to turn that off. So now you can see the nodes. And then I'm going to switch my view around and simply choose my nodes here at the end of my beams. So now those are up there, all the node numbers. And yeah, click OK. And now you'll see that those rigid links have been created between my beam and my column, connecting the two. And so yeah, now my columns and my beams are connected. I would like to do the same thing for my other columns. So with these columns that are supporting the beam here, we have again that pin connection. So we want to add the rigid links, or we want to add member hinges to the rigid links that we create. So we'll create another nodal link definition. And yeah, when you create these, you can see them on the left-hand side here. You can name them so you don't get confused which one is which. But again, we want to search for members. And this time we want to add a member hinge in. Now you could argue whether this member hinge, so it should be applied to the top of the column or to the end of the nodal link. I'm just going to add it to the start of the nodal link. Yeah. And yeah, so now I have my member hinge definition, rotation about the local Y and Z axes are released, so moment. I'll click OK, and then click OK again. And I forgot to highlight the nodes. So yeah, we want to select our nodes, that's important. And click OK again. And yeah, now we have our rigid links with our member hinge here, releasing the moment connection between the rigid link and the column. And so now we want to do the same thing for our coupling members. I'm going to check on just only my coupling members. So let's create another nodal link definition. I'm going to select all of my coupling members and click OK. Oops. And now, yeah, I've created links for my coupling members to link to the columns. So we can go around and double check that all of them are correct. Okay, so you can see here we have a little bit of an issue with this nodal link. Hopefully that's easy to see. Yeah, so you can see this one. If I activate or show hidden objects, you can see what the issue is. So my X bracing, the link is linking to the X bracing, which is closer than the node that's on my column. And so this is where the option exclude objects comes in. So we want to exclude that X bracing. And so I'm going to have to activate my X bracings and highlight that X bracing, click OK. And now that rigid link has gone to the column node instead. So yeah, that's one way to use those. And I also want to do the same thing for the coupling members up here. I don't need to create a new one. I could just include these coupling members within the same definition. So I'm going to highlight those nodes. I highlighted my X bracing as well, or no? No. There we go. And yeah, so I want those to also connect to the beams. And again, you can see these are all good, except yeah, you can see some of my coupling members are connecting to my X bracing. So again, what I want to do is exclude that X bracing from being selected. So I'm just going to choose all of my X bracing to exclude from that nodal link. And yeah, so let's double check. So yeah, all of my coupling members are now connected to my center beams here with that eccentricity and no longer connected to any of the cross bracing. So that's good. And next, we want to do the cross bracing. We want to connect our cross bracing to the nodes on the columns here. And yeah, so I'll create a new nodal link definition. And this time we don't want to choose members, we want to choose nodes because we want our cross bracing to all connect at the same node here on the column. And so yeah, we will choose all of the nodes for our X bracing, like so. Click OK. And now again, we're going to have some issues with the X bracing connecting to the closest node, which is our coupling members here. So we want to exclude the coupling members now from this definition. So if I go back and I hide my cross bracing and only show my coupling members, and exclude those from the X bracing. Click OK. And yeah, if I exit out of, I'll just cancel out of this visibility now. And so yeah, we can go around. We can see now the X bracing is connected to that same node there. Yeah, so those eccentricities are there. All of the X bracing up here is all connected to the right node. Yeah, it's all good. So now everything is connected. And the last thing again that we want to do, just like before, is change some member types. So I'm going to change this to cross section or member type. And I would like to assign my cross bracing to the tension member type. So I can highlight those and just edit them and turn, oops, not truss, tension. So now those are pink. And I'll do the same for my coupling members. Double click on those and change them to truss. And we don't need to add any hinges to our columns in the center because they already have those hinges defined. Yeah, so we have our member types defined. Now we want to add in, again, our supports. So we'll add in our hinge supports down here. Catch just those nodes at the bottom of the columns, like so. And now we can run the self-weight calculation and double check that our results look good. So we'll run that. And I'm going to turn on section colored. And there we go. Okay, so yeah, now we can see the deformations. We can see they're a little bit different now that we have those eccentricities defined. We have a little bit of torsion on our outside beams here. We can just check the deflection and the Z direction. So if I increase the deformation here a little bit, we can see what that looks like, a little exaggerated, and it's similar to the analytical model. Only difference is now we have those eccentricities kind of, in essence, applied to this model. But yeah, the max deformation we're getting is around 0.4 inches. So then we can also check our member internal forces. Again, we can see our axial forces, and we can view our moments again on our frames here. And again, we're seeing our negative moments in the center where our columns are connecting, and the positive in the spans there, which is good. And so yeah, this is comparable to the analytical file that we use with the doable link, but instead we just imported this as an IFC. And yeah, I'd just like to give some additional info. We also have the same links now, but for lines. So if I go under types for lines, we have line links, and you can use these for walls and slabs, and they can be connected in the same way. For future development, we are testing a tool that will allow you to create these links automatically, but it is not ready to be shown yet. So hopefully it will be released soon in the future. So look out for this. And if you're interested and want email updates on when this will be available, please feel free to contact us and we can provide those updates for you. You can also look out for development updates under your extranet account on our website. And yeah, so this workflow can be an alternative to the direct link. It's great since CAD programs can import and export IFC files. You can also leave the beams basically where they are with these eccentricities, because these eccentricities would have had to been added in anyway. And the benefit of this is that for the steel joints add-on, you would have had to add these eccentricities in anyways. And yeah, so if you wanted to add a joint in here for the coupling members to the beams, you would have had to add that in anyways. And also the additional benefit of the IFC file is that the BIM info is also saved now within the objects. So if I double click on one of these members, you can see that we have this BIM tab here for the member. And so yeah, all of that BIM info is saved here with the global ID or the GU ID, and our cross section and material is saved within there as well. So yeah, I could just export this. So in RFEM, you can also export IFCs. So we can go to export IFC, click OK. I'll just rewrite one of my files. And then I can go into the BIM viewer. And I think I exported only that member I had selected. You can just export simply only selected members. So I'll save that again. BIM viewer. So I could just open that file. And yeah, this is the file from RFEM that we just made. And I can, again, click on the member, and I can see that material info and section info saved within that file, along with the same GUID here. And the good part about this is that because we saved that info in the IFC, we can use that info again, like I just did with the export. And the members, like I said, save the GUID. And this is good because it allows all of us to compare IFC files. If we have two IFC files where the GUID of the objects is the same, this will allow us to compare sections and materials, which is good. And in the future, we would like to include the export of our steel joints and reinforcement in the IFC format, concrete reinforcement in the IFC format as well. But this is something we are still working on developing. And the goal is to have a properly looking IFC file exported from RFEM 6 with all of the proper information that is necessary. And so that is all of the workflows that I wanted to show for today. And I thank you for attending and for your attention. And I will hand it back over to Amy now.
All right, perfect. Thanks, Alex. Maybe since we have a few extra minutes, we'll do something that we don't normally do. We'll talk a little bit about some of the questions that came up during this presentation. I did already send a response for everyone to see for most of these questions, but maybe just to reiterate some of these. So one of the questions is, do you have a joints check to ensure that web doubles or similar are not required for the steel structure? This is something that our steel joints add-on is capable of, where we would hone in on one of the connections for the steel structure. So not necessarily the member design, but taking it a step further for the connection design. And then we could determine if the web was stiff enough, if we needed stiffeners, if we needed doubles, whatever that may be. Another question came up was, what is the purpose of this IFC import as opposed to the direct integration for Revit to RFEM? I think the intent of the IFC for a couple of reasons. Number one is, outside of Revit, there's many other BIM programs that we could potentially integrate with, but we don't have a direct integration. And most of those are going to support an IFC file export that we could read into the program RFEM. Additionally, for this particular scenario and Revit specifically, the direct integration does require that both Revit and RFEM are installed on the same computer. So if there is a situation where possibly a drafter is on one computer and an engineer is on a different computer, we're not going to have these direct integration capabilities. As far as we know, there's no export of the analytical model from Revit, so therefore we would export the physical model as an IFC. So this is what Alex had showed with the import into RFEM. Unfortunately, the downside of IFC is, of course, our physical model. Things are not fully connected. So therefore, we showed how to connect those elements with those rigid links. With that, kind of a follow-up question, with so many rigid links in the model, does this provide incorrect internal forces in the members? So I know there are other FEA programs out there that if we are applying many rigid elements, such as rigid links, it can suck up forces and really affect the calculation itself. In RFEM, we don't have this problem. These rigid links are purely used to transfer the member end forces from one member to the adjacent member that it's connected to. We're not going to see those rigid links affect the stiffness or provide incorrect results with the analysis. Furthermore, they don't have to be rigidly connected. We can apply member hinges to release the moment or control any of the member fixity. Another question that came up with the rigid links is how to define effective lengths for the members. By default, the effective lengths, when we do carry out the design according to the AISC for the member or the CSA S16, we can set this to default to the full member length, which would be node to node, not including the rigid link. This may be sufficient, and we can also, of course, take into consideration members that are framing into that member to decrease the effective length to something smaller than end to end. If you want to also consider the rigid link, it's entirely possible to override that effective length or these unbraced lengths to account for that additional distance. So that's all possible as well. So with that said, we'll go ahead and wrap up the presentation today. I do see maybe a couple more questions came in, so we'll certainly follow up after the presentation to you directly through email. If you enjoyed the presentation today, you are interested in testing out maybe the Revit integration with the RFEM 6 trial, you can contact our sales team in our Philadelphia office. So you can scan this QR code here. This presentation was uploaded to the GoToWebinar, so you'll find that PDF of the PowerPoint. Also, our contact information is shown at the bottom of the screen here. So our phone number to the Philadelphia office, and also our email address is info-us@delubal.com. Okay, so we also want to let everyone know that we will plan to have more upcoming webinars in the new year in 2026. So this will be the last one we have of 2025. You can keep an eye out directly on our website to register for those under support training webinars. As most of you know, I will send out a reminder email about a week before these take place, so you can sign up directly through email. PDH certificates will automatically be emailed to all participants who were here for this full presentation. So that is a requirement of the states that we are pre-approved providers, that you are here for the full duration of this webinar in order to receive that PDH. If you did watch with a colleague or in a conference type setting and you yourself did not register for the GoToWebinar, you will need to request that PDH by emailing us here at info-us@delubal.com. Again, if you yourself did not register with your own name and your own email, you were here for the full presentation, let us know who you watched it with. And again, please send an email to info-us@delubal.com. The PDHs are not automatically sent out as soon as this presentation ends. It usually takes us about a day or so to get those together. So again, those will come directly to your email. And with that said, I want to thank everyone for attending today's presentation. There will be a short survey that pops up when we do end this presentation or when you do log out. Would love it if you could give us some feedback on the webinar today or any of your other thoughts with RFEM or our products that we offer. And as always, we hope to see you at our next presentation. Thanks so much.